maybe you've had such an investigation yourself or family members. In this, this is a big magnet, very strong magnetic field, and we can generate magnetic resonance imaging, MRI images, with this technique. Here you see the image of two upper legs. This is the inside of the bone marrow that is right in this part, and again, cross-sectional image was taken. Here you see bright adipose tissue and a muscle which is quite dark here. So the question is, why do we see this contrast? From the bone itself, you get no signal. It's the black, and inside the bone is the bone marrow, which is also lipid kind of structure, which gives you also bright signal. So this is MRI with the same physical principles, which I will explain a little bit. It's only a very short time, so I will only explain a little bit. With the same physical principles, we can also get a spectrum. In MRI, in images, you mainly look at the signal from water, and in the spectrum, you can look at signals from different metabolites. So this gives you anatomical information, and this spectroscopy gives you some chemical information, looking at what kind of metabolites are here. Okay, so what do we need? We need a strong magnetic field, which is inside here is a big coil with a strong current, and you know that the current in a coil is inducing a magnetic field. Then we also need coils to pick up the signal and do the measurement. I will explain in a moment how this is used. And we have all kind of, it's actually a sort of antenna to pick up the signal, of course. And there are coils for all different parts of the body. This is a head coil. You also have it for extremities or bigger coils for measurements. Okay, so I already said the tunnel, which is seen here, opens a bit, is a big coil, and it's made from superconducting material, so that means that the resistance is very low, it's zero. So very little energy is lost when you have a current through this coil. To be superconducting, it needs to be cooled to a very low temperature. But in that way, we can get a magnetic field strength that is 100,000 times the magnetic field of Earth. And that's important. We need this to do the measurements. So what is it actually? What are we using? What's the basis of these measurements? In the human body, there are a lot of protons, especially in water and fat, and magnetic resonance imaging uses the signal mainly from water. And from the water, it gets a signal from the protons, because from protons have a positive charge, and it has a characteristic that we call spin, and that means that it behaves like a small magnet. A proton nucleus behaves like a small magnet. So when we place it in a magnetic field, the spins align with the magnetic field. That's why it behaves like a small magnet, so it aligns with the magnetic field. And now the funny thing is that it can have two directions, either up or down. And the interesting thing is that one of these positions is a little bit more favorable. So when you place these nuclei or spin in a magnetic field, you will get a little bit more alignment in one direction. So that means you get a nettomagnetization. This nettomagnetization is very small. From like 1 million spins in a 1 Tesla field, 3 more spins will have the up direction than the down position. So you see that this is a very, very small magnetization that we want to measure. So that's the challenge. Okay, so we have a difference in the number of protons that have parallel or anti-parallel direction when you place them in a strong magnetic field, but it's only about 3 per million at 1 Tesla. And this increases with a stronger magnetic field. The clinical scanners, the older ones are mostly 1.5 Tesla scanners. Newer ones are also 3 Tesla scanners. Depends a little bit on the application that you want to do, what is better. But you see that with a stronger magnetic field, you get more nettomagnetization. A little bit more are in the optimum down position. Okay, and yeah, so this we leave for the moment. And now we have a problem because we have a very strong magnetic field and we have a very small nettomagnetization that we want to measure, and they are in the same direction. We cannot measure this because it's a very small difference. So what we want to do is we want to have this small nettomagnetization, which we want to take out of the way of the strong magnetic field from the scanner. And this we can do by applying radio frequent poles. I come to this in a moment. So this is electromagnetic radiation interacting with the magnetization, pulling it out of the direction of the magnetic field. So here is the direction that this is what we call the Z direction, is the direction of the strong magnetic field, where we also have the nettomagnetization. And we want to take it out of this plane into a plane perpendicular to the main magnetic field. Because there we can, if it's there, we can also measure small magnetization. Okay, so when we have spins outside the magnetic field, they're just random oriented. When you have them in a magnetic field, they align with the magnetic field a little bit more in one direction than the opposite direction. And when you take the magnetization, and they also have a certain frequency, and when you take this magnetization out of this Z direction, they will start to precess. And the precessing motion is just like a toll, so it's going like this, right? Okay, so what we want to achieve is we have first a nettomagnetization in the direction of the scanner. We cannot measure it, we want to take it out of this plane, we want to take it in a plane perpendicular to the strong magnetic field where we can measure it. And this changing of the orientation is called excitation. And we do this by interaction with a radio frequent pulse. Okay. Assume we have it there, we have it in the plane perpendicular to the main magnetic field. We have a magnetization that is precessing with a certain frequency. So how can we now measure it? We have a changing magnetic field. If we put here a coil, which is basically circular geleidend materiaal, so it's possible to have current through it. It induces a current in here, changing magnetic field, induces a current right? Okay. And how big this current is depending on how big the magnetization. So in that way, we can measure the magnetization. The nettomagnetization that was very small, couldn't measure it in the Z direction. Put it out in a plane perpendicular to the main magnetic field, and then we can have current induced in a coil, and that's our measurement. Okay, in that way we can detect this small magnetization. That's a signal here, how we see it in the coil. We have an amplitude that is changing because the current has a certain frequency, and you also see that we lose the signal after a while. It's decreasing. Okay? Okay, we said this in the direction of the scanner. This is also what we call the B0, the main magnetic field. We can measure it. We measure it in the transversal plate. We can measure the transversal component. And we get this by applying radio frequent pulse. And it's measured with a coil, so a changing magnetic field. Changing magnetic field is inducing a current. It's like the dynamo on your bike. You have a small magnet that is moving, so you have a changing magnetic field inducing a current. And why is it magnetic resonance? So where's the resonance coming in? Resonance means that you excite the system with the same frequency as the natural frequency. So it's like with a swing. If you have to tilt somebody with like 50 kilograms, you would need a lot of force. But if you have it on a swing, and you always keep a little bit of energy, but in the right moment, you can actually use low energy to get the same done, right? If you have, if you're working with resonance, so always giving the force at the right moment, you can use lower force because they're adding up. And so if you look at this one first. So if you look at the electromagnetic radiation that is used, so the pulse that we give to change the direction of the magnetic field, you will see that with MRI, you use a radiation in this range of energy. If you see here, this is logarithmic scale with the frequency. So the higher the frequency of electromagnetic radiation, the higher the energy, right? If you look at X-rays, for example, they have a very high frequency, they have very high energy. Now the problem that you get there is that you have ionization is taking place because it's such high energy. When you go to lower frequency, the visible light, microwave, and MRI here is actually quite low in energy, but because it's using the right frequency, it can be that low in energy. Just to say, why is it magnetic resonance? It's because you use the frequency of the nuclei themselves to get this tilting of the magnetization out. Okay, so resonance, we have the excitation with the same frequency as the natural frequency. So in the case of magnetic resonance imaging, we have an oscillating magnetic field with a certain frequency, which is the frequency of the spins themselves, which we also call the Larmor frequency. And in that case, the protons can absorb energy, and then they can change the magnetization can change direction. It depends on how long we apply this pulse and how far magnetization will change. So by choosing a certain duration of the pulse, we can get it in the perpendicular plane, and then we have a 90-degree pulse, we see. If we take it longer, we'll again go out of the plane. So I said we have the coil which generates a magnetic field with a certain frequency to change the orientation of the magnetization. That's the excitation. We also have the coil to do the measurement, where the change in magnetic field will induce a current, which is actually your measurements. So you use coils for two things. One coil is to get the magnetization out of the main orientation of the magnetic field, and the other coil is to receive the signal. So the changing magnetic field will then induce a current in this coil, which is your measurement. This can actually also be done by the same coil. Sometimes it's different coils, sometimes it's the same. Okay, so if we want to have an image, we also need a certain encoding from what is coming from where. I will not focus on this. This is being done by gradients, but it's out of the scope of this lecture. I will talk about the image contrast. So why do we get different signals from different tissue? And this is because we saw that we have a decreasing signal in the coil that is receiving the signal, that is actually doing acquiring the measurement. You see that it's decreasing in time. But not for every tissue it's decreasing in the same way. And this we can use, so these differences in relaxation, we can use for the contrast. It can also be that the proton concentration, water mainly, so that the water concentration is different between tissues. This can also give you a contrast. Okay, once more, a little bit different depicted. We have the nettomagnetization to start with. We have a radio frequent pulse. Okay, in this case we give a 90-degree pulse. We have the magnetization in the plane perpendicular to the main magnetic field. And here it will relax again. You will lose this signal. It's decaying signal. We call this relaxation. And this we will measure. And actually there are two different relaxation mechanisms. One is called T1 relaxation and the other one is called T2 relaxation. Now what's the difference? The T1 relaxation means that, okay, you have your begin moment where you have some nettomagnetization in the direction of the magnetic field. That's energetically the best conditions. That's with the lowest energy. That's the equilibrium state. Now you do something, you apply a pulse, you get it out of this equilibrium. If you stop the pulse, it will slowly return again to the equilibrium. Okay, so that's just returning to the equilibrium. It also means that energy is actually dissipated in this process. Okay, so if you look at this way, that's the direction of the main magnetic field. You tilted it in this plane, with the precessing magnetization here. When we stop the pulse, it will return back to the equilibrium position. And if you now look at this relaxation in different tissues, you see that it differs. So in fat, for example, it relaxes quite quickly if you compare it to cerebrospinal fluid. This is mainly water, and you see that everything that has like structure, big molecules, is shortening the relaxation time. So if you have pure water, the relaxation time is very long. So CSF is a lot like water, it relaxes slowly. So here we have differences, and we can use these differences to get the contrast. So, okay, here we directly after the 90-degree pulse. Then a little bit later, still later, and this is in the very long time after the pulse, where it's back at the equilibrium. Now the T2 relaxation is how fast your signal decreases in the plane perpendicular to the main magnetic field. And this you can imagine when you start your measurement, you bring this magnetization in this plane. They all have the same, these spins all have exactly the same frequency. But then after a while, there are small differences in the frequency. And when you have small differences, it means that your signal is not completely in phase anymore. It's like with the chorus, if you have this children's song, if everybody has exactly the same speed of singing, you can understand these words, right? Then it's nicely it's synchronized, it's in phase. Now if some people sing a little bit faster and others sing a little bit slower, you get out of phase. And the signal is blurring. And the same happens with the magnetization. First you have exactly in phase measurement. You have a nice current with a high amplitude in your coil. And after a while, because you have a little bit faster frequencies, a bit slower frequencies, it will get out of phase. You will lose the signal. It can also be shown like this. First you have a nice in phase, and then after a while you get this dephasing. And this, the red arrow is the resulting intensity that you then have. And this is then getting smaller and smaller because of this dephasing. Also the T2 relaxation. So this process is different in different tissues. And that's what we want to use, because all the differences, everything that's different between tissues can lead to a contrast in the image. Okay, so in this case again you have fat and cerebrospinal fluid, and also here the relaxation of the cerebrospinal fluid, which is mainly water, is slower. So we have slower dephasing. The signal is longer, nicely in phase in the CSF, and it dephases more rapidly in the fat. Okay, and how can we now get how can we get this to work for us? How can we now get contrast out of this? We have a certain moment where we do our measurement, which is what we call echo time. It's going a bit too far why this is called echo time, but we have a moment where we say, okay, now we want to know what the magnetization is. And if we do this this moment of the measurement, this echo time, we can choose it here where these differences are biggest. If we wait for a very small, very short time, we don't have a lot of, and then you don't have a lot of T2 contrast. So then even if T2 relaxations are different in these different tissues, you will get similar signals if you don't wait. If you wait for a little while, you get differences. So if you measure here, you will get low signal for the fat, and you will get high signal for the CSF. So the intensity here will be higher than for the fat, right? So you get contrast. But you have to choose your moment of measurement in the right way. So in this case, you see here a T2 weighted image, and let me see. So here the cerebrospinal fluid has a high intensity because it's still there. The magnetization is still there. In the fat, it has already decreased. So here you have fat under the skull. And here it's decreased already. Okay, so that was the T2 relaxation. We have to choose the moment of the measurement. The same is true if we want to take advantage of the T1 relaxation. Now, how is this? You have to be aware that one image is not only one application. You have to excite a lot of times before you have an image. So you have an excitation, you have a measurement, and you wait a little bit before you do the next excitation. And all these excitations then add up to one image. Now the question is, how long should you wait? I mean, if you wait for a long time, it takes a long time. What is happening in the time that you wait? So first you have the magnetization in this direction. You bring it in the base perpendicular to the main field here, and it goes. If you then look how much magnetization do I have here in this direction, it's 0 immediately after the 90-degree pulse because we all took it out of this direction, right? So it will be 0, but slowly it's going back to the equilibrium position. And after a while, you have your magnetization back in the Z direction, so in the direction of the main magnetic field. Now you have to do different acquisitions for one image. Now you can say, okay, I wait a little bit, and then I do my next acquisition, my next excitation. Or I will wait for a long time to do my next you wait for a long time, it means that all the magnetization would relax back to the equilibrium situation. It also means that you have a lot to excite. Your magnetization is completely back as it was in the beginning. If you only wait a short time, it's only a very little magnetization here. We also say the spins are still saturated. They are not back to the equilibrium. And you can only bring in the plane perpendicular to the main magnetic field what is there. If it's not there, you cannot bring it in this plane. Okay, so and if you now have differences, differences in the T1 relaxation, for example, in the 0 prime fluid and in that, with CSF having a slow relaxation and have a fast relaxation, you can see here what is happening in the Z direction, so the direction of the main magnetic field. First, your magnetization is here. You give the 90-degree force, it's vanishing. Slowly it's returning to this situation that was there in the beginning. In this case, you wait for a long time until it's completely back. You start again, your next excitation. It relaxes back. Here you see what you can actually measure in the XI plane, so in the plane perpendicular to the main magnetic field. There is first 0, but at your 90 degrees pulse, you get magnetization in this plane, and it will slowly decrease because we have decaying signal. So the fat is decreasing more rapidly than the CSF. So in this situation, your T1 doesn't play a role because you wait so long that all the magnetization is back at the equilibrium. Now we can also do this here. You can say, okay, I don't wait for such a long time. I will wait only a short time. And what you see there is that, okay, one metabolite is already relaxed completely, but the other one is not. And then you will give your next excitation. And so, and if you don't wait for such a long time, you will get differences in intensities because one tissue, the magnetization in one tissue is already completely relaxed, and the other one is not. And if it's not relaxed, you don't have so much to excite, so the signal is smaller. Okay, so here you get contrast based on T1 relaxation. Yes, is this still clear, or is there something I have to repeat? I will go on and just stop me if you lose it. I will. It's coming back. Those three examples. Okay, so here, so we can have different sequences. We can say, okay, we can make.
Ik weet gewoon zeker dat als ik me nog echt 1 dag in zoveel type, dat ik het beter college zou helpen.
Okay, I want to have T1 contrast. I want to have T2 contrast. And the other thing that is also possible is that you say, okay, I want to have proton density ratios. That means that T1 and T2 are not playing a role. I don't want to have contrast that is based on different relaxation kinetics. I want to have contrast based on the content of protons. So I want the tissues that are bright. I want to have the tissues that have a lot of protons, I want them to be bright. So these are the three contrast mechanisms that we can use. If you look here, what you see here is the magnetization in the direction of the main magnetic field. First, you have it there. You have your, before you start your experiment, if you place this equation in the scanner, you will get this mental magnetization in the direction of the main magnetic field. But then you get the 90-degree force. Then the magnetization in the direction of the main magnetic field is 0. But slowly it will return to the equilibrium. And it differs on the tissue how fast that this happens. Now if you want to have T1 weighting, or if you want to have contrast based on this T1 relaxation mechanism, your repetition time should not be too long between the excitations. So you have an excitation here, and here you would already give the next excitation, because then for this metabolite you only have little magnetization to excite, and for the other ones you have a lot. So then you would get differences in contrast, in intensity. Now, if you want to have it T2 weighted or proton density weighted, you don't want to do this. You would then wait for a longer time in between excitations. So then you would choose for a long repetition. On the other hand, what should you do if you want to have a T2 weighted? Here is T2 relaxation is about the disappearance out of the plane perpendicular to the magnetic strip. So here we look at the magnetization in the plane perpendicular to the magnetic field. So this is what the coil is picking up. That's what we are measuring. Now the magnetization immediately after the 90-degree pulse is high, and then slowly it's vanishing. We saw that this signal is decreasing in time, right? In the coil. Okay, so the amplitude of the signal is decreasing. One is faster than the other. If we want to have a contrast based on these differences, we should choose a time of the measurement here somewhere where you have these big differences. Right? If you don't want to have these differences based on T2 relaxation, you should immediately after your pulse, you should measure. Here, the signal didn't have much time to develop these differences. Okay, so for T2 weighting, your echo time, your time after the measurement, should be long, or in the range of the T2 of these measurements. The range of the T2 relaxation time. If you don't want to have a T2 weighting, you should have a very short delay until your measurement is actually taken. So these are the formulas. We skip these, but this is actually resuming what we just said. If you want to have proton density weighted images, so the more protons are there, the more intensity we have. The repetition time should be long, because that means that we don't have T1 weighting, and the echo time should be short, because it means we don't have T2 weighting. If you want to have T1 weighting, your repetition time should be shorter in the range of the relaxation times of the tissues. And your echo time, you want to choose it very shortly, because your echo time determines how much T2 contrast you have. In the T1 weighted images, you don't want to have T2 contrast. If you want to have T2 contrast, pure T2 contrast, your repetition time should be long. So in between excitations, you wait until all the magnetization is back to the equilibrium. But your echo time, so you have your 90-degree pulse, and then the question is how much delay do you have until the measurement? And there you want to be in the range of the relaxation time. So to get an idea, this is now at 1.5%. What are these relaxation times? We give it these relaxation times in a time until 60% of the magnetization is relaxed. So T1 in muscle is about 870 milliseconds at 1.5 T. When you see, okay, adipose tissue is much faster. So if you have a T1 image, you can nicely defer these two tissues. Right? The same is actually true for T2 weighting. For muscle, you have quite a short T2, and for adipose tissue, it's longer. Okay, not very handy, but something is wrong, but the adipose tissue has a longer T2. So there you also get differences, and very extreme it's with the CSF. with very long relaxation times for T1 and for T2 much longer than the other tissues. This is the summary slide, but maybe we first go to with an example and then back to the summary slide. So now, if you look at a brain, you have a CSF here, and you see that if we have a T1 weighted, the CSF to start. Now, T1 weighted means that the repetition time is not so long. So we know that the relaxation time of CSF is long. So if we choose our repetition time short, it means that the CSF is not completely relaxed back to the equilibrium, right? So that's why we get a little signal here. And the brain tissue is already relaxed back, at least to a bigger extent. That's why you get more signal here. Now, the opposite is the case if you do a T2 weighted image. Then you see your CSF is bright. Now, why is this? It means that if you do T2 weighting, you have your 90-degree pulse, having the relaxation, the magnetization in the plane perpendicular to the main magnetic field, and then you wait a little bit. Now, the tissues with a short relaxation time the signal will decay more rapidly than for the ones with a long relaxation time, like the CSF. So if you have a little delay until your measurement, it means that you lose signal in these tissues here, and you lose very little in the CSF. That's why this signal here is strong, intensity is strong. If you go to the proton density weighted image, you see that the contrast is much less in this case because water concentrations are not so different actually. And in this case, you have a very short delay, not to have any T2 wave. So for all the tissues, you get a high signal, and you wait for a long time, but all the relaxation, no matter how long it takes, is actually relaxed. Okay, so maybe this now makes more sense. So if we have concentration and weighted proton density or concentration is the same because the concentration of the protons, of course, that makes signal. If you want to have proton density weighting, you choose a long repetition time to make sure that everything is relaxed back, and the short echo time, short delay of your measurement, to make sure that you don't lose much signal, and that you don't lose it differentially depending on the tissues. Now, the T2 weighting, you choose a long repetition time because you want it all to be relaxed back. You don't want to get these differences depending on the one relaxation. But you choose echo time a little bit. So you choose a bit of a delay to allow dephasing of the signals in some tissues and not in others, so that you get differences depending on the tissue. If you want to have T1 weighting, your TR should not be too long, because you want to have the T1 relaxation time, that is the time that it takes to relax back to the equilibrium concentration, determining your contrast. So the tissues that relax back very fast will be bright, because they have a lot of signal. The tissues that take longer, you will have lower intensity. And what is long and what is short? We can go as the delay to a measurement can be a few milliseconds. This depends on the hardware of the system. And long normally is more than 1.5 seconds. Okay, is this clear to everybody, or are there parts that I should explain again? Then I will come more to the clinical applications. Because what we can do, okay, we have a nice contrast in MR, and that's the nice thing, that you have good soft tissue contrast. If you have an X-ray, you can nicely see the bones, but the soft tissue, you don't see much of it. And with magnetic resonance imaging, you can get good contrast between muscle and fat or other tissues. You can even change your sequence, your protocol, in order to maximize the contrast between the tissues that you want to see. So that's the nice thing with MRI. You can also add contrast agents to make it even more powerful. So if you have a contrast agent that is shortening your T1 relaxation time, it can enhance the signal. So normally, this is a T1 weighted image here of a brain, and actually here is a tumor. But you see that the T1 relaxation time of this tumor and the surrounding tissue is quite similar. So you don't have a lot of contrast. If you use a contrast agent in the plasma, you can inject it in the bloodstream that is shortening the T1. It means that the magnetization in the blood will very rapidly relax back to the equilibrium. So even with a short repetition time, you will always achieve complete relaxation. So that means that you have high intensity of the bloodstream. If there is a tumor, it's the case that the blood vessels around the tumor get leaky, so you have extravasation of plasma. So here you can that's actually so this is the image with the contrast agent. Here you can see that there is more intensity in the region of the tumor, and that's because everything that is plasma you now see very bright, because you have a contrast agent in the blood that is shortening your T1. So on the T1 weighted image, everything that is blood is very bright. And because you have leaky vessels here in the tumor, you now see that there is a tumor. Now, instead of doing a T1 weighted image, you do a T2 weighted image. You can see that the T2 relaxation times of edemas are very long. And around this tumor, there is also edema. The tumor is here, and here there is an edema. And this you can nicely see on T2 weighted images, right? So T2 weighting means that once you have your magnetization in the plane perpendicular to the main magnetic field, it will decrease. For some tissues, it will decrease faster than for others. So you wait a little bit until you do your measurement. And this time that you wait allows differences to develop. So that means that for edema, the magnetization is decreasing very slowly. You lose very little signal, but for surrounding tissue, it decreases rapidly. So there you go. Okay, so the nice thing is that you can choose your contrast. And most of the time it's not pure one, it's not pure T2 or T1 weighted image, but you also have pictures. Another example is if you look at cardiac tissue, shortly after myocardial infarction, if you do a T2 weighted image, maybe I should explain first. This is the left ventricle. Actually, if you look from the top of the heart on it, then you have here the right ventricle, and this is the left ventricle. You see this is the muscle wall, the thick wall for the left ventricle, where the pump blood through the whole body, and the thinner wall for the right ventricle. And so bright here is the blood inside the heart. And here there was an infarction. You can see it schematically here. Here you have increased intensity in the T2 weighted image. This is blue on this scheme. Now, what you can also do to make an infarct visible is that you give the contrast, as I said, so gadolinium contrast is decreasing your T1, meaning that blood is getting very bright. And it also makes intensity of infarcted area brighter. So here you can see, okay, here it's brighter from here. So here was my infarct. This is the infarcted area. And then it's always important to look at, is it complete? Is it through the whole muscular wall, or is it only on one side? Because the prognosis is much better if it's not the complete wall that is affected. And the interesting thing now, combining these two measurements, is that with the gadolinium enhancement, you can say, okay, this is really infarcted area, which is now white here. But with the T2 weighted images, you can detect a somewhat larger area with increased intensity. And this is blue here. That's not really infarcted, but it's the area at risk. Because after an infarction, damage can sometimes increase to much further extent. So in this way, you can say, okay, this is area at risk. This is really infarct. Okay, so that's a bit how you can use these images. And now, I also want to talk a little bit about magnetic resonance spectroscopy.
Oh, yes.
So in the beginning, I said, okay, it's with the same physical principles, also with this electromagnetization, that you want to bring in another plane to have it measured, and relaxation mechanisms. The background is all the same for the spectroscopy, but instead of getting an image, an anatomical image, you can get chemical image. So for the imaging, we mainly look at water. And for the spectroscopy, we can actually look at different metabolites. And it's possible to do this not only for protons, but also with other nuclei that have a spin, so for phosphorus and carbon-13. Carbon-13 is the natural abundance of this isotope is very low, it's only around 1.1%. The normal isotope of carbon is carbon-12. But for proton and phosphorus, these are the main isotopes. So we can also look at other nuclei. And here you actually see a phosphorus spectrum of skeletal muscle. And you see that the highest peak you get from a phosphor metabolite, phosphocreatine, which is an energy buffer, to generate ATP. These three peaks are the ATP peaks because it's adenosine triphosphate. So every phosphate group gets another peak. And here is the inorganic phosphate. Now if you start doing exercise, you use ATP. But what you see is that these concentrations actually stay completely stable. You use ATP, but apparently at the same time you regenerate ATP at the same speed. But what you then see is that the PCR peak, the phosphatic peak, is decreasing. So this is your energy buffer. And you can see this real time happening in an MRI scan. You can do phosphorus spectroscopy. But more like clinical examples, you can also use spectroscopy for some clinical questions. There are metabolic diseases with certain enzyme deficiencies, for example. So, for example, creatine deficiency is reported. This is really very bad resolution, but this is a proton spectrum of the brain. And what you can see here, this is the healthy spectrum. You have here cholines, and then you have here the creatine peaks. Now, in a deficiency of creatine, you can see that these peaks here are much smaller, or not there at all. And in this way, you can, for example, monitor a certain supplementation with creatine, for example. You could look at how much of this peak is coming back, because you can determine the metabolite concentration in vivo. Another example is prostate cancer example. A bit a different technique that you cannot, you can get spectra from different regions of interest. So every square is giving you a spectrum. In this case, also proton spectroscopy. You can see the different spectra here. And here you can have two examples of a healthy spectrum and a spectrum in a tumor. And what is known of cancer is that the choline peaks are elevated, for example, and also that the cytokine peaks get very low. So these can then be markers of tumors. In principle, it would also be very valuable to have a sort of cancer staging, because you have different cancers that are more aggressive than others, and what you have to do now is take a biopsy, and this is a tool that could provide the information that you need. The clinical practices is that it's not yet in the clinic. I mean, the potential is there, definitely, but it's not a standard clinical practice yet to do spectroscopy only for certain questions like enzyme deficiencies and for research, but it's not in the standard clinical practice. Now another example is liver steatosis. So this is the accumulation of fat in the liver. Here you see a spectrum if you do NMR at high resolution. So in a ex vivo or just for chemical structures, you have very high resolution, and this is oil. So this is the spectrum basically of the fatty acid. You have here CH3 peaks, CH2 peaks, and different proton signals depending on the position in the fatty acid. Now that would be nice if we could detect this in vivo. Now in vivo the resolution is much less, but we can see these two peaks. So if you look at the spectrum here, a bit bigger, you can see, okay, this is the CH3 peak, this is the CH2 peak. So we can see the same signal. We can also see the signal of water. And then from this we can calculate like a fat-water ratio. And this is now an example of a healthy individual. If you look at somebody, spectrum of somebody with a fatty liver, you see that the lipid peak relative to the water peak is much increased. Here in the healthy subject, you can hardly see it. Only when you will enlarge it, can be seen. So this is also a clinical example how it could be used. But also liver steatosis is normally still detected with echo, although the sensitivity is much lower. So magnetic resonance spectroscopy is much more sensitive. But it's not used in clinical practice yet. It's also quite an expensive measurement. Imaging models. Okay, so mainly MRI is used. MRS, not really, although it does have the potential. There, but okay, so that was MRI. But well, what I want to say about MRI is the contrast is based on A, concentration differences, so how many protons are there, and B, very importantly, the relaxation mechanisms in the different tissues. And for the relaxation mechanisms, we have two relaxation mechanisms, T1 and T2 relaxation, that we call the protocol in the right way, we can maximize one versus the other component. And we can also use computations like gadolinium-based computations that shorten the T1, and so make the blood in T1 way, which is very important. For MRS, important to remember that it's the same physical principle as for MRI, but we can also get chemical information, so we're not limited to anatomical information. MRI is mainly using the characteristics of water in different tissues. With MRS, we can actually measure concentrations of different metabolites. And it's possible for different nuclei, protons, phosphorus, and carbon. But in the clinical setting, it's not really used. I hope there are a lot of questions.